Hey guys, in this video I will present a solution to Bulgaria National Math Olympiad 2022 problem 4. Firstly, we'll have a look at the statement. Let n be an integer greater than or equal to 4 and x1, x2 up to xn be real numbers. We also define their indices to be cyclic with period n, therefore let xi plus kn just equal to xi. If there exists an a greater than 0, some real number, such that xi squared is equal to a plus xi plus 1 times xi plus 2 for all I between 1 and n, then we shall prove that at least two of the sequence members are negative. In such a situation, where we want to consider a sequence and show that it can't just be positive or non-negative real numbers, we could take a look at what would happen if all the sequence members were non-negative real numbers. So let us consider what the given equation tells us if xi plus 1 and xi plus 2 are non-negative real numbers, for example. Plugging these values into our given equation gives us the following. So if we assume xi plus 1 and xi plus 2 to be non-negative real numbers, then this implies, firstly, what is given, xi squared is equal to a plus xi plus 1 times xi plus 2. And now, because both are non-negative real numbers, we know that this is greater than or equal to a plus their minimum squared. And furthermore, we might just get rid of the a to say that this is all greater than the minimum of xi plus 1 and xi plus 2 squared. Now, if we recap what we have, we can take the square root after all of this, which is quite nice, and we get that the magnitude of xi must be greater than the minimum of xi plus 1 and xi plus 2. We label this equation 1. Now I want to make a second implication from this right here. I'm going to write this down because there's another interesting thing that happens in this case. Because, okay, let's take a look at this. If something is negative right here, then the right side could take all the values between 0 and positive infinity. It can't be negative due to the fact that we have an xi squared on the left. But when both are non-negative real numbers, then this product is also non-negative. And therefore, we get xi squared is greater than or equal to a in this case, or rather that the absolute value of xi is greater than or equal to the square root of a, which we label equation 2. Okay, so now I just wanted to get the immediate implications of the problem statement out of the way right away. We know that 1 and 2 must always be true. By that I mean the entire implication. The right side is not always true, but if the left side is true, then this follows, and the same goes for 1. Now we take a look at what we've got so far. And right away, when looking at what 1 tells us, we should get suspicious. Because if we imagine this as some non-negative sequence, then what this tells us is that whenever we have some index I, and then we have some value xi, but then we will get some even smaller value xi plus 1 or xi plus 2, and that cannot always be true intuitively. We can formalize such an intuition using the extremal principle. Let's consider some xk such that its absolute value is minimal within the sequence. Then this can't really be true. In particular, we know that the absolute value of xk is less than or equal to the absolute value of xk plus 1, and the absolute value of xk is also less than or equal to the absolute value of xk plus 2. And of course, if those two were positive or non-negative real numbers, we could just remove the absolute value signs. Therefore, this side of 1 is not true for k, and therefore 1 implies that xk plus 1 is less than 0, or xk plus 2 is less than 0. So since we can always find such an xk with minimal absolute value, this tells us our sequence always has at least one negative member. Now we have got something out of this approach. We know that we get one sequence member, but we want a second one. Now it seems unlikely that using this same technique we will get another such solution, but maybe we can use our first negative sequence member as a starting point to generate a new one. So we know by what we have said here that there is some r such that xr is less than 0. From this we will try to find other sequence members that are negative as well. And at this point I want to mention something that we are going to do. So basically what we have given here is not one condition but many conditions, in fact exactly n of them. And therefore we might expect, and that is what we're going to have to do to solve the problem, that if we take such a local approach, that we're going to have to substitute this condition many times, which might get a little bit spammy, but therefore in such a problem it is important to maintain an intuition for what is happening so that you know at what point you should introduce another one of these equations to get to a further point. We're going to do a proof by contradiction. Therefore, assume xr is only negative sequence member. Because n is greater than or equal to 4, this tells us, for instance, but those are going to be important values, but what this tells us is that the values around xr are going to be positive, so or non-negative. Xr minus 1, xr plus 1, xr plus 2, and xr plus 3 are all greater than or equal to 0 because they can't be the same index because our length of cycle is n, which is greater than or equal to 4. By equation 2, this tells us that xr is less than or equal to negative the square root of a because the two next sequence terms are non-negative, therefore the absolute value of xr is greater than or equal to square root of a. Furthermore, because xr plus 2 and xr plus 3 are also non-negative, we can do the exact same thing for xr plus 1. Thus, 2 tells us that xr plus 1 is greater than or equal to the square root of a because it is non-negative. So I talked about knowing when to substitute which equation, and at this point we see that we have nice bounds for xr and xr plus 1. We take a look at our original equation and see that it would be nice to have those two terms on the right because this tells us something about the previous term. And that's exactly what we're going to substitute. We can now say that xr minus 1 squared is equal to a plus xr plus 1. But since this is negative and this is positive, we get that all of this must be less than or equal to a plus negative square root a times square root a, which is less than or equal to 0. And we already noted that xr minus 1 is greater than or equal to 0, and therefore this implies xr minus 1 is exactly equal to 0. Therefore we will have equality in both of those inequalities. Therefore xr must be exactly equal to negative square root of a, and xr plus 1 is equal to square root of a. This we can substitute again in our given equation. Therefore, choosing r for I, we get that a is equal to xr squared, which is equal to a plus xr plus 1, xr plus 2. Since we know that xr plus 1 is equal to the square root of a, which is positive, it follows, okay, so first of all, the product xr plus 1, xr plus 2 is 0, which is just exactly what we have right here, and therefore xr plus 2 must be equal to 0. Now, therefore, xr plus 2 is also a very interesting sequence member because it has a small absolute value. And if we take a look at what 2 tells us, this cannot be true for r plus 2, and therefore 2 implies that either xr plus 3 or xr plus 4 is negative. But we already know that xr plus 3 is greater than or equal to 0, and therefore we get xr plus 4 less than 0. Now we have what we wanted exactly, a second sequence member that is less than 0. Therefore, we are done for n greater than 4, because in that case, I've said multiple times, the cyclic period of those indices is n, and for n greater than 4, r and r plus 4 are different indices. But we still have to look at n equal to 4, because then what this tells us is just that xr is less than 0, which is what we already know. Okay, so the last remaining case is n is equal to 4, and in that case we know that xr is equal to negative square root of a. xr plus 1 is equal to the square root of a, and xr plus 2 is 0. That we already have. But now xr plus 3 is equal to xr minus 1, because n is equal to 4, which is also 0. So we have exactly all of the sequence members. Either this works out and what we have to prove would be wrong, or there's some contradiction between these 4 values for dxi. And in fact, it turns out that this doesn't work, which is good, because then our proof is correct. Because if we plug in r plus 2 for I in our original equation, that gives us 0, because xr plus 2 squared is equal to 0, is equal to a plus xr plus 3 times xr, which is 0 again, because xr plus 3 is just nothing but 0. This is a contradiction as well, and in any case, we are done with our proof.